So, next talk is going to be about Blackwells and the future that we will have with them. So I'm inviting Adam. Adam, please, stage is yours.
Thank you for inviting me. Hello, hello. Hopefully you can hear me okay. Yes. Watch out for the step. So I was invited quite some time ago to join this event, and the request from the organizing team was to talk a bit about the differences between Hopper and Blackwell GPU architectures. Yes. But I thought to myself, you can download spec sheets from our website. So I still wanted to stick to the topic that we were given, but I decided to approach it in a slightly different way. So I will not be talking about memory speeds and streaming microprocessor counts. Instead, I'll try to explain to you why we have designed Blackwell the way we did. Yes. And what does it mean to the workload? So my name is Adam. I've been at NVIDIA forever, and I've been in this privileged situation to see like our AI technology grow from zero to where it is today. About 15 years ago, I've decided to look at what seemed at that point of time as a fairly obscure problem of neural network scaling. So how to make neural networks bigger and how to train them on larger data sets. Today, I lead a cross-European, cross-EMEA AI team that works with our key customers to make sure that we understand how people use our technology, and I'm working with engineering to help them design both of our hardware and our software correctly. So Blackwell is faster, yes, but that's not because we've made the silicon 30 times larger, or that's not because we've made the frequencies 30 times higher. We did that as well, but today I want to talk about some of the things that we had to do to get to those numbers, and hopefully you will find that interesting. And I think it's important to cover, yes, because I fully appreciate that some of the things that we are introducing into our systems are not immediately obvious. And we kind of have this conversation over the last 10 years now. Every time we release new generation of GPUs, we add new capabilities that allow us not just to keep up with Moore's law, but significantly exceed it on occasion. So we had a variant of this talk before. Yes, when we've introduced in 2016 DGX, so the system that then transformed into HGX specification that all of you use. We've introduced this NVLink interconnectivity, and people ask why. Why did you do that? Tools to train across multiple GPUs do not exist. Yes. At that point of time, TensorFlow barely existed and didn't have any implementation for distributed training, at least not a good one at that point of time. PyTorch definitely didn't exist. But we had to create it because we believed that neural networks can get better only when they get bigger and they're trained with larger amounts of data. A year later, we've introduced our first data center designs. Again, people ask us, why did you do that? At that point of time, there wasn't a single library that could train across the boundaries or between servers. We had to work with the likes of Uber to develop tools such as Horovod. Similarly, when we've introduced mixed precision, it wasn't because people were shouting at us, we need reduced precision arithmetic in order to build our neural networks. No, we've introduced it because we truly believe that, one, we can make the training stable with reduced precision arithmetic, and that was something that would allow us to simply double the performance of our systems, and we continue to do things like that. So in this talk, I want to focus on the key things that we've done with Grace Hopper, Grace Blackwell, and that are quite significantly changing the way neural networks are being built, and gives you dramatically different, dramatically higher capability when it comes to their design and execution. So I guess to summarize, what we typically do is we don't build GPUs because neural networks look like that. Instead, more frequently than not, neural networks look like that because of the constraints of our GPUs, and today I'm going to talk to you about a bigger box for that watermelon. Does it make sense? Okay, so we had this variant of this talk already, and a lot of them are recorded. In fact, I wasn't aware of it, but almost exactly 7 years ago, I've delivered a variant of this talk downstairs, in the room in front of the buffet. So if you want, just Google for TensorFlow Meetup. And we'll continue doing them. We'll continue talking about how and why we enable people to build larger and more complicated neural networks. And there is a good reason for that. I think we have very hard evidence to show that we still will benefit significantly for larger neural networks. Neural networks trained on larger data sets. For those of you that haven't seen this graph before, this is an extract from a technical report from Meta Llama 3.1 paper, which effectively shows that as we've been observing over the last almost decade now, we continue to see improvements with the increase of neural network sizes and data sets. So today I'll talk about what we can do to keep up with that relentless growth in computational demand from our AI research colleagues. But I'm also going to talk about the generalization of those laws. So something that was quite obvious to us, what seems to be more obvious to the broader AI community, is the fact that the same laws apply at inference time. So I don't know how many of you have heard, but it turns out that by taking neural networks and allowing them to compute for longer, they can be quite dramatically improved as well. So today we'll focus not just about what we've been doing to help people with large-scale data-intensive training, but we'll talk also a bit about future of inference and new challenges that especially test time, inference time compute brings us. So with Grace Hopper, Grace Blackwell, we've introduced a number of critical innovations that, on top of making the silicon faster, give us that number that I've showed you on the first slide. The first one of them that I want to discuss today is C2C connection. How many of you know what a C2C connection is? That's good. That means that I'll cover something new for you. So I'm not sure whether you've ever had a look at how our latest generation GPUs are designed, but it turns out that they are designed considerably differently than the previous generation of GPUs. In particular, we have noticed that there is a huge added benefit of not just controlling the GPU itself, but actually controlling the design of the CPU as well. That is why quite some time ago, and they've been on the market, especially for some HPC customers for a while now, we've introduced a new family of CPUs based on ARM architecture called Grace. Yes. What makes those CPUs different from traditional x86 CPUs is the fact, there are a couple of things, but the one that I want to focus on today is the fact that there is a cable between that CPU and a GPU that is much, much thicker than the PCI Express bus. Yes. So we have a dedicated connection between the CPU and a GPU that allows us to just move things faster. So you might say, hey, how is that useful? This is still the same GPU, so it will still run at the same speed. And you're right. Like the way this is helping us accelerate training and inference, it's not obvious until it's obvious. So yes, it's still the same GPU. But suddenly we can, in fact, use it in a different way. So we can carry significantly more on exactly the same GPU because just of the presence of that cable. How? Well, it does require changing the way we work a bit. So if you think that you will take a neural network that you've built today on Hopper and you'll move it to Grace Blackwell, and suddenly you'll be able to automatically take advantage of that interconnect. That's not necessarily true, at least not right now. You will have to restructure that neural network. But if you choose to do that, the benefits are actually quite considerable across the board. They are considerable when it comes to training, fine-tuning of neural networks. So just because of that cable alone, you can get quite dramatically higher training performance, and the same applies to inference. If you think about how modern transformer-based inference is organized, and if you redesign it ever so slightly, you can squeeze out significantly higher performance of the same GPU. So what those plots are showing, they are showing comparison of x86 and Grace-based systems together, both using the same GPU, demonstrating quite dramatically different performance in their capability. So what are the types of things we can do? Let's go through some of them one by one. So let's start with training. Let's start with, maybe even before we dive into training, with a recap. So as I've mentioned, we now have this additional connection between the CPU and a GPU that operates over NVLink, so delivers 900 gigabytes per second of bandwidth. And this allows us to do a couple of different things. One, it allows us, as I mentioned earlier, to move things much faster between the CPU and GPU. And secondly, as a consequence of that, it significantly extends the total amount of memory that we have if we're smart about how we're using that memory. So suddenly, CPU memory is not just this slow, very remote thing that we have to use very cautiously because of the bottlenecks of the PCI Express bus, but suddenly we can truly utilize the entire bandwidth of the onboard memory system. Of course, it's not as fast as the high bandwidth memory that we have in the GPU, but it's now dramatically faster than it was. And this is what I mean by dramatically faster. If you have a look at the black and gray bars versus the green bars, you will immediately notice the difference. So what does it mean to you, to people that are practitioners, that are training those neural networks? Well, you can try to think about what you do with your intermediate calculation in a slightly different way. So normally, when you would be training large language models or other large neural network architectures, and you'd be short on memory, what would you do? You might destroy some of the intermediate activations during the forward pass because you don't have space to keep them, and you'll accept the fact that you'll have to recompute them. Yes. And that would allow you to save some memory bandwidth and memory storage in exchange for compute. Since those models are predominantly memory bound, the compute is close to being free, so that was a traditional way of doing it. But suddenly, with this additional C2C interconnect, we in fact have enough bandwidth to keep up with the compute and move some things out. So rather than keeping the activations in GPU memory during the training process, before we start calculating backward, we can evict some of them to the CPU memory just to bring them back in time for the backward pass. So you might think that, how does that help? Well, it helps in many different ways, and I'll go through them one by one. By the way, this is already implemented. So if you want to play around with it, that's already implemented in quite a few different libraries, including our Megatron, including in Transformer Engine, and including in, there's a variant in Hugging Face library as well. As long as you don't want to have fine-grained control over how and what is evicted, its usage is relatively straightforward. Just have to pass a couple of flags to turn it on, and then to decide how big of tensors you'll be evicting from the memory at any given point of time. So again, this is available in Megatron, in Transformer Engine, in Hugging Face, some experimental code. Feel free to play around. It can, depending on your workload, it can make a significant difference. How significant? Well, those are experiments on Grace Hopper, not yet on Grace Blackwell, but this graph demonstrates the difference between exactly the same GPU, H100 in x86 and in Grace configuration, and you can see that that leads to about 25% acceleration between the architectures. So 25% of a speed difference on exactly the same GPU, just because you have a thicker cable. Yes. So not trivial at all. But you can do other things as well. So this was a use case where you would try to take advantage of the additional bandwidth not to do activation checkpointing, but you can do all sorts of other interesting things. For example, when doing training that is not particularly computationally expensive. So I don't know, training adapters, yes, or maybe doing minor continual training of those neural networks. When you're executing a job that is not constrained by time, execution time, but more by memory, suddenly, by enabling those offloading wrappers that I'm demonstrating here again, this is one of the examples that we've published. You can train models that would not normally fit on a single GPU or on a handful of GPUs on a much smaller number of GPUs. So on this plot, what you will see is comparison of an 8-way x86 server, training in this case Llama 270B, to the performance of single, 2, and 4 GPUs. So of course, a single GPU will not be faster than 8 GPUs. But it also is not 8 times slower. Notice that the single GPU execution on this diagram achieves 67% acceleration in the execution time. So not only you can train on smaller amount of resources, but in total you burn through a smaller number of GPU hours. Of course, the wall time is longer, but it's not 8 times longer, it's just 4.7 times longer. So I think there are a lot of advantages to people that train at very, very large scales, as we showed in the previous slide, but also those of you that are doing early experiments, maybe at smaller scales, you can also benefit from the capabilities of that system. And I think this encapsulates only the first wave of our ideas on how to use that additional connectivity that you have. And we'll see more. Asynchronous checkpointing was mentioned here earlier. That's also one of the things that will benefit from having that technology available. The same applies to inference, and we can suddenly use very similar things at inference time. So we can effectively do things such as persist KV cache more effectively. For those of you that don't know, most of the modern transformer architectures are autoregressive, meaning that when they execute, they don't just get data in and give you an output, but instead one has to iterate over their execution many, many times to get the output that you need. And KV cache is a mechanism that allows us to not to do redundant computation during that process. A lot of KV caches on modern systems are very repetitive. So people genuinely tend to ask the same types of questions. So if you're smart about how you maintain that KV cache, how you move it, you can once again achieve quite significant acceleration of execution. So if you find a good way of persisting KV cache in either CPU memory or even moving it to an external system for storage, you can see quite significant benefits of doing that. And if you have a look, once again, the fact that you have that additional bandwidth between the CPU and GPU can lead to quite dramatic acceleration. Have a look at the difference between the middle column, which is the performance of x86 H100 system, to the Grace-based system on the right. And again, code is available. It's been available for quite some time. In TRT LLM v0.9, we've already introduced that capability, and people are already using that because it directly translates to your bottom line. So every token is a cost for you if you're hosting your own application, and this allows to reduce it quite dramatically. And again, the implementation is available both in TRT LLM. For those that don't know, TRT LLM is a foundational library that we provide to the community to optimize inference of neural networks, but also via other ISVs who use TRT LLM as a backbone of their implementation. It's also integrated into countless other serving libraries. There are also other things that you can do at inference time in the same way as we've offloaded parameters during the training process to fit our Llama 70B into a single GPU. We can try to do that, to do the same thing on Grace-based architecture, because once again, we have enough bandwidth to do that. Yes, so we can evict weights from GPU memory to the host memory, or even further in some situations. Again, code for that is already available, so do have a look if you think that your application can take advantage of it. This is going to be beneficial, especially for those that might have a lot of different neural networks with smaller amount of traffic. You can do some very interesting things with that. This doesn't necessarily give you obvious acceleration at the same latency budgets, because in effect, as long as you're targeting lower latencies, you will be bound by other factors. But if your application is processing data at batch, then you can operate with much higher latency budgets and quite dramatically improve your throughputs. So if your application doesn't care about latency, you can benefit from tricks like that quite significantly. There is a fundamental difference between 60 tokens per second and 100 tokens per second. Is the same difference as between $60 and $180. So do take advantage of some of those tricks if your application can take advantage of it already. And again, the code is available now. You can play with it today. I know that this crowd might not care about databases, but this also this technology can have a non-trivial impact on performance, especially on in-memory database systems, and so yeah, quite significant speed up depending on the workload. But now that people are more and more seriously thinking about how to store, persist KV caches for longer periods of time, it already has quite significant impact on performance of some of those workloads as well. Okay, so that's C2C. Yes, don't be that guy. Yes, if you have access to Grace-based systems, whether that's Grace Hopper, that's unlikely in this group, or Grace Blackwell, as was mentioned here. Nebius will have one of the first systems based on that technology. Do take advantage of some of those capabilities. They will make a significant difference to your code. And the code to make some of those things happen is already available, and it's already tested by quite a few customers, especially on Grace Hopper platform across the growth. It makes significant difference. Yes, and there are more innovations in that space ahead of us, especially when it comes to implementation of asynchronous checkpointing, very large multi-LoRa deployments. So it's not uncommon for some of my customers to have systems that have, I don't know, a couple hundred different LoRa adapters that they need to juggle. That adds tremendous amount of value, and further more complicated KV storage and decoupling inference capabilities. So to summarize, C2C, we have higher GPU throughput, higher bandwidth cache for system memory through unified memory, and the software that takes advantage of it in AI is coming to existence. Okay, so that's one thing. That's one major thing that we designed differently in Grace Hopper, Grace Blackwell. This feature is specific to Blackwell. This is not something that is specific to Grace nor Hopper. With Blackwell, we have introduced new numerical representations. Yes. Well, how interesting is that? Well, it should be interesting because, as we've discussed earlier, going from 8-bit precision to 4-bit precision allows you to hypothetically double the performance of your application, or halve the cost, depending how you want to measure it, or do twice as much work. You might have seen this slide in some of our earlier Blackwell decks, which was not very helpful, accelerating throughput with intelligent 4-bit precision. It wasn't particularly useful because it didn't actually describe all that much in a lot of detail what that intelligence stands for. And the secret sauce here is that word here in the middle called microtensor scaling. So what we haven't done, we haven't just introduced an FP4 numerical format. One, that wouldn't be particularly interesting. And two, it wouldn't be particularly useful. FP4 numbers are too small in themselves to do anything useful with them unless you use trickery. So what we've done exactly that. We've used a trickery that you can use obviously for inference, and we've published already some benchmarks discussing FP4 and FP6 inference that you can have a look at. But more importantly, it can also help with training. How, you might say? Well, as I've mentioned, those are not just FP4 formats. So we didn't just take a standard floating point definition and truncated it to 4-bit. As I mentioned, that wouldn't be particularly valuable. I don't think there is a good way of actually making training work with that. Instead, as I've mentioned earlier, we've introduced so-called micro-scaled data formats. So many of you know that with Hopper, we've introduced 8-bit numerical representation, FP8, and that allowed you to train in somehow stable way. You had to do a bit of work to make it work well, but the stability would be achieved by allowing the system that we've called transformer engine to rescale those 8-bit numbers. The challenge there was that you would be able to rescale those 8-bit numbers only within the boundaries of an entire tensor. And a tensor is a massive and a potentially structure with a lot of numbers, a lot of which will not fall into the numerical range where you have representation. So in Blackwell, instead, we've introduced micro-scaled data formats that provide an additional shared scalar variable, that x here, for smaller blocks of data. So in contrast to Hopper, where there was one number per tensor, now we have one scaling factor per block size of 32 numbers. So imagine having a tensor, slicing it into tiny blocks of 32 numbers, and each and every one of them has its own scaling factor, allowing us for more stable training. Can you train with those smaller numerical values? Well, yeah, in theory you can. So it takes a bit more effort because you have to especially maintain the transposed matrices, because once you rotate those blocks and things don't line up particularly well. So there is some trickery involved, but in fact we see early evidence that you can make things converge, and that it behaves in a very comparable way to higher precision training, hopefully potentially becoming the new golden standard for training and inference. So yes, again, once you manage to get your hands on some of the Blackwell GPUs, and if this is something that you care about, if kind of your core business depends on your ability to train faster, please reach out to Nebius, to us, and we'll help you force it to work for your neural network. So that's the second major thing that we've introduced. The third one that you might have heard about is are changes to NVLink. How many of you know what NVLink is? Amazing. So for those of you that don't, NVLink is a communication bus. I've mentioned it earlier, that in terms of its purpose, principle, is very similar to PCI Express. Yes? It's different in many ways. First and foremost, it's an order of magnitude faster. It also allows you to manage memory in a slightly more convenient way. But until recently, we would have systems that were designed around 8, or in some special cases, 16 GPUs. So you would, 99% of systems out there would allow you to connect 8 GPUs with that bus, effectively creating a limit to the number of GPUs that would have very high bandwidth. Yes. All of the other communication would have to happen over InfiniBand or other network technology. We've invested a lot into making sure that it's as fast as possible. That is why we have one GPU one NIC per GPU, as Gleb told Gleb a second ago. But now we have 72. Yes, so with the Grace Blackwell generation of GPUs, 72 GPUs can be interconnected together with NVLink, creating possibility for completely different neural networks. And since clearly we're very far away from the end of the scaling clause, it seems unavoidable that we'll see larger neural networks, and that will require that connectivity. despite maybe popular belief, I don't think we're far away. I don't think we're close to exhausting humankind's repositories of data. If you again look at some of the technical reports, this is again from Meta, you can see that there's still a lot of wiggle room, not to mention that most of the data sets that we use, even in just large language modeling, are predominantly English. So I think there is a way to go. So as a consequence, it's extremely likely, and we in the last weeks, and that was confirmed already a couple of times, that we'll see even larger neural networks trained on dramatically larger data sets. And effectively, what this new system allows us to do is to change the shape of that box, allowing for completely different neural network designs. Yes, what those neural networks will be, it's very difficult to say. That is why in the technical documentation that we publish, we try to focus on those that are very likely to be successful. So this is a plot that we've published last year focused on mixture of experts performance. And again, this is not because this GPU per se is 30 times faster that we achieve 30x speed, but it's a combination of all of those factors that I've mentioned earlier. In this particular case, since mixture of experts are very expensive in terms of network communication, a lot of it is down to that extra networking capability. So we will likely to see much wider neural network architectures, like mixture of experts, but also wider mixture of experts. But even if we don't see mixture of experts succeed, and it is possible that we will not, bear in mind, mixture of expert models are not a new invention, yes? So we have had a couple of tries at them. I think there is a huge likelihood that we'll see much broader neural network architectures that will significantly benefit from having more network connectivity. But it's also likely that they will be successful, especially given how good of a job DeepSeek did recently at forcing them to work. And in effect, I think this is one of the first pieces of work where a mixture of experts architectures are on par with densely connected models in terms of accuracy, and there's a huge chance we'll see more of them, as a consequence making this system ideal for this type of workload. But even if not, there is also a huge demand now for neural networks with significantly larger contexts, and that's also something that this broader NVLink interconnectivity will allow us to do. But it's also not obvious that they need to be wider, and potentially there might be other ways of hiding communication. They will be definitely useful in shaping the way neural networks of 2026, 2027 look like. And counterintuitively, those systems might be ideal for inference. Why? People might associate inference with this benign problem in comparison to training, whereby you just take a neural network, you throw something in, and the answer comes out. But this is not the case with modern neural networks. Modern neural networks, whoa! So there's a section here that it doesn't matter. Modern neural networks do significantly benefit from test time compute. So how many of you know what test time compute is? Yes? Oh, that's good. So for those of you that don't, it turns out that if you encourage neural networks to run for longer, if you allow them reason, if you allow them to be executed in parallel, they can provide dramatically better answers. And I think this type of a system with such a dense interconnectivity between the GPUs will allow people to really go crazy with deep thinking, allow those reasoning neural networks to think for very long periods of time, and we already see evidence of that. I think a couple days ago, BBC published a short article describing a researcher from University College London that was doing some research on bacteria antibiotic resistance, and in that case they were executing inference not for milliseconds, not for seconds, not for minutes, but for hours. And I think in coming months and days it will not be unusual unusual for people to send very important problems, very important reasoning problems to those machines to reason for days, weeks even. Yes, whereby a large system like the one that I showed is devoted to that problem and that problem alone. And if that comes to fruition, those will be ideal systems for this type of a workload. So with that, I'll open to questions. 3 things. Yes, new CPU architecture and new connectivity, new numerical formats, and much broader NVLink domain. Thank you. I think there are some questions, but there is also a microphone. So if we could pass it around, that would be greatly appreciated. Who is the mic bearer? Here we go. Thank you kindly.
Thank you. I just wanted to ask a clarification about the first thing you said, C2C. Is that available for Blackwell as well? What's the difference between the two, if there is any? You would be helpful to clarify that.
Sure. So over the last 2 years, we've been deploying Grace Hopper systems, but they landed predominantly in higher education systems. Yes. So those are not extremely broadly available. With Blackwell, they become effectively mainstream design. And so whenever you hear Grace Blackwell or GH, this refers to not just a system that coincidentally has Grace and coincidentally has Hopper, but it has this joint system that have this very thick interconnect between each other. There is a lot of other trickery involved. For example, they're capable of sharing power budgets and juggling it depending on the demand. And so you can think of them as a single system. That is why we don't refer to them as Grace plus Blackwell, but Grace Blackwell. It's a single thing from our perspective. There are 2 more questions here. I don't know who could pass the microphone.
Thanks for the talk, great talk. So my question is, it's great that the bottleneck of CPU to GPU transfer is being addressed,
Sure.
But another bottleneck that is very painful is the bottleneck between GPU memory and the chip. And we can obviously work around that by being very creative in inventing IO.
Yeah, sure.
Like flash attention would be a great example, but you can only push IO-aware algorithms so far. So I'm wondering, what's the NVIDIA's long-term vision in addressing this particular bottleneck?
Well, so I don't think faster memory systems that are external to the GPU exist. Yes, and we try to stay on top of it. That question has a very long and rather complicated answer, and it's a multidimensional answer. One aspect of it we've covered today, looking at new, more innovative numerical representations for neural networks. And I think this is not the end of the road by any means. I would strongly... Have you ever heard about a gentleman called Bill Daly?
I'm afraid I didn't.
So Bill Daly is one of the heads of our research, and he has a series of lectures on Stanford University and a couple other events where he dives into all of those considerations. So if you were to listen to that lecture, he goes through all of the things that we are considering. I'm not sure I can comment on which of those and when will find their way into our architecture, but we are quite open about the ideas that we have. And it's not a singular problem. It's a multidimensional problem, and we try to address it from all sorts of different perspectives. Yes, both in terms of the core silicon design, both in terms of doing better job at code level, trying to find some of those tricks with smaller numerical representation. We're chipping away at it from all of the different angles all at once. And yes.
Cool. Thanks for the talk.
Sure.
So I've got a question about NVLink. So you have fast interconnect between Grace and Hopper, or Grace and Blackwell,
Sure.
and between the Hopper and Blackwell chips.
Sure.
Do you have any plans to connect the Grace chips with a similar interconnect?
So first and foremost, we have this thing called Grace superchip, which is effectively 2 Grace chips interconnected together, but also individual Grace chips are interconnected, depends on the design of the system.
But is that through PCIe or?
No, also NVLink.
Okay, thank you.
Sure.
Thanks for the talk.
Sure.
I just wanted to ask, it's a general question about model drift. How do you contend with model drift here when you're paying that compute penalty when you're retraining your models?
So model drift is specific to non-stationary problems, yes? So to problems that change in time. Some things, they just don't change in time, or they change in time so slowly that you don't have to care about it, yes? So dealing with model drift in some problems, I don't know, development of traditional recommender systems or development of models that deal with financial trading is a dreadful problem. Yes, you have to, first of all, notice that you have a problem, and then use some sort of a rolling window approach to try to intervene, retrain, continue training, revalidate. And that's very painful. But a lot of problems, they just don't, they are not affected by that. Yes, in principle, like human language doesn't evolve as quickly as you might think. Yes, it doesn't evolve from Monday to Friday. It takes significant amount of time for language to evolve considerably. Human knowledge, does it evolve? Yes, but it turns out that those larger models actually absorb new information very quickly. They're extremely sample efficient. So almost every kind of national laboratory in Europe has a project on large language model continual training, and that's actually surprisingly easy for those larger scale neural network architectures. So depending on the problem and the set of algorithms used, that has a tendency of changing from being dreadfully difficult to childishly easy problem. So I don't have a good answer for you, I'm afraid. I think there is another gentleman here, and
hello.
Still have 2 minutes. Yeah.
So, just one question on confidential computing
Sure.
on the Blackwell.
I didn't discuss it, but it's there.
Yes, okay.
And it's fine.
Are there any upgrades from the previous architecture?
Well, this is not my core area of expertise, to be honest with you, so I wouldn't want to speculate. If you're interested, I can introduce you to a colleague in my team called Mohawk that can answer those questions. But it's still there, yes. The software is still relatively early, yes, so getting it to work is potentially not the easiest of feats, but we have a couple of customers that are using it very successfully, and if you have a problem, we can get you in touch with Mohawk and he can guide you through the process.
Thank you.
And there was one more person. I think we still have a bit of time.
Hello, thank you. I just wanted to ask, how does Blackwell handle AI inference workloads on real-time data?
On?
Real-time data.
What do you mean by that? Like
the data set which you are using, apart from Hopper, what is on the data used by Blackwell?
So I'm not sure what's the nature of the question you're asking. So real time means many things to many people. Yes. So what I can tell you is that most of our GPUs eventually find their way into embedded platforms. Yes, and they can be used for, say, hard real-time safety-critical applications. So yes, you can use them for that. Engineering for real-time execution is challenging, though, especially when you have high stakes, but it's definitely possible. Bear in mind, a very large proportion of automotive self-driving car solutions are based on our platform. Similarly, very large proportion of robotics applications. So yeah, you can have the GPUs execute hard real-time. It is an engineering task, yes. But we do have tools for that. So we have our Drive platform and Metropolis for intelligent video analytics, and also a robotics framework. So depending what exactly is it that you want to achieve, you would approach the problem in a slightly different way. Happy to answer further if you can clarify, saying that I think we're a couple of seconds out of time, so we maybe could take it to break.
Thank you, Adam.
Thank you.
That was really impressive.